So PLS discriminant analysis, as you can see, first of all, it's based on the other method that we already know very well. It's a PLS regression. And you can also see that it's actually a discriminant analysis. So it allows you to discriminate between classes, right? Well, the algorithm is rather simple. First of all, we don't have any y values. We don't have anything to predict in this case. And you remember, for regression, we need to predict y values, right? What we do, we simply create artificial y values, a dummy y values. For example, if you have two classes, and it's actually advisable to use PLSDA mostly for two classes, for discrimination between two classes, you simply set y values to -1 if object, for example, belong to one class, and +1 if object belong to another class. Or you can think about belong or does not belong to a particular class. That's it. So now you have y values. Now you can create a PLS model that will predict these y values. Of course, although our y values are binary, -1 and +1, the predicted values will not be binary. So it means that the predicted values can be like -0.8 or +1.2 or similar. So what we need to do is just to make a threshold, to use a threshold. So every time we have a predicted value, we compare it with 0. If it's positive, it's a member. If it's negative, or for example equal to 0, then it's a non-member. That's it. You can see it's a very, very simple thing. Again, we didn't need any new method. It's just a PLS regression with a little bit on top of that. It's this creation of this dummy y variable and using threshold for classification. Okay, this is an example. Again, I use our iris data set. What I did here, I used the two classes, Virginica and Versicolor. You remember they're overlapping. For example, I set -1 for all samples in my calibration set which are from class Versicolor, and then I used +1 for samples from the class Virginica. And then you can see I used -1 and +1 for my original reference y variable, but the predicted y variables, you can see they vary quite a lot, right? But they vary around the true value, so you can see this is 1 and this is -1. The variation is around this -1 and +1. That's good, yeah. And then what you can see is that most of the red points, the ones that have +1, they are positive, right? This is the threshold. So this is a threshold. And most of the blue points, they are negative. So we have only 2 points that were misclassified. It's the 2 points from the Versicolor that have positive predicted value, y value, and they will be classified as Virginica. Yeah? So this is the classification results. You can see the plot very similar to what we have seen in Simca case. So you can see that this is Versicolor, this is Virginica. You can see the legend. Then you can see indeed we have two Versicolor objects that were misclassified as Virginica. So strictly speaking, for Versicolor we have 2 false negatives, and for Virginica we have 2 false positives. It's a bit simple in this, or maybe even tricky for discrimination, right? For discrimination. Okay, so what else we can do? First of all, it's a PLS regression model. So it means that all PLS results are included. You can see the x distances, so you can find outliers. You can see regression coefficients, which objects are important, which objects are not important. Again, you can see that the biggest regression coefficient we got, it's for these two, which is the petal length and petal width. You can see it's approximately -1 here, while this one, for example, it's like 0.6, right? So you can also look at the variance, how much of y variance it explains. Also, it's a bit misleading here because we have binary values in y, but still we can do that. So you can see, again, 2 components explain most of the y variance. Yeah? And then you can see the RMSE, root mean square error of prediction. So we simply take this, the predicted y value from this -1 and +1, and then take a sum of squared distances, average it, and take a square root. So you can see, again, it seems like 2 components is optimal in this case. And what I showed you here, it's all the, for example, the error is for cross-validation, and the variance is for calibration set. Okay. So all PLS results that you already know very well, you can also show them and investigate them for PLSDA model. Plus, of course, there are a lot of things on top of that. You already seen this prediction plot, but you can also, for example, make a lot of other things. I didn't show you this, but you can also do it in Simca. You can show the confusion matrix. I think I will demonstrate it in the next video where I show you how to do things in R. But you can also, for example, show sensitivity plot, specificity plot, and misclassified plot, how these 3 statistics depend on the number of components, right? Again, you can see that, For example, if you use misclassified, you can see that we got the smallest number of misclassified objects for the cross-validation set if you use 2 components, right? With 3 components, it's a bit larger here, right? You can also see that we got a very good specificity if we use 2 components, right? For example, for cross-validation, specificity is a little bit smaller in this case. Then we have also very good sensitivity when we use 2 components, right? So it seems like 2 components is indeed the optimal here. And you remember this is discrimination, so it means that if you, for example, apply your PLS model to objects which do not belong to any of these 2 classes, you will still have misclassified. You will still have classification. You will still arrange all these measurements to one of the classes. What I did here, I applied my PLS model to test set, and you can see that all these objects from the test set were classified as Virginica, but all these objects were classified as versicolor, although we have these setosa samples here, right? And this is a bit tricky. So in this case, right? So remember that this is a discrimination, not the 1 class classification. So make sure that when you apply model based on 2 classes, discrimination of 2 classes, you don't have objects from the other classes. Of course, you can use, for example, the distance plot to see that these objects actually do not fit the model well. So you can identify them as outliers. But remember to do that. Okay. So that's actually it. Now you know everything about how to use also projection-based method. Not everything. I think I told you like 10% perhaps about all the possibilities that you have. But this 10% enough to actually to start using these methods for your own data, and then you will learn more via actually the experience, and also try to read all the modern papers related to, for example, in this case, to classification. New methods appear every year, sometimes even faster. So I highly recommend you, if you want to use chemometrics, if you want to make chemometrics as one of your important tools in your toolbox, you should follow also the publications. And when you use software like R or any other programming languages like MATLAB and Python, one of the advantages you have, you can implement all the modern methods instantly, right? You don't need to wait until a big company, a big software company will implement it. You can try them yourself immediately and then find out if they are actually have any advantage for your data. Okay. So that's it. And then in the next video, I will also show you how to do things in R very quickly. There is, of course, a function PLSDA. You provide it's very similar to PLS, but instead of y as a vector of values, you need to provide c as a vector of factors. And then the same things, if you want to use test set validation, use predict, but you need to provide both the measurements and the factor with known classes. If you want to make prediction for new variable, for new set of measurements, you need just to provide the set of measurements. Okay. And then all the plots that you used in Simca will also work on PLS, and plus, of course, all PLS plots will work as well.